results I can see there. Should we start?
Yes.
Okay. So let me share you my slides. Here it is. Yeah, yesterday it was a constant head method or constant head permeameter to measure the hydraulic conductivity in the laboratory condition. So it was clear that we are measuring the discharge Q for a particular time T. Just a moment, please. Sorry. Let me close the network so that I'm not getting disturbed when taking class. Okay. Now, so we are observing discharge from this sample. This is basically the core sample we have taken from the soil without disturbing the soil. It is fitted inside this arrangement of a jacket which has two porous plates which allows water without any restriction and supply of water with a constant head here. Head is maintained. So the flow which occurs through this soil is because of this head difference H. So simply we are observing discharge Q in time T. Soil has a cross-sectional area of A here, and then we can simply by using the Darcy's relationship, V is equal to minus Ki. K is hydraulic conductivity, I is delta H by delta L. So L, we know that this is sample size. We can find out if it is Q, then it will becomes A into V, A, and this is for time T. This is not instantaneous discharge. This is total volume generally we are taking here. So we can find out the value of K as here. Discharge which is measured, length of the soil sample, length of the water passing through the soil, area of the sample, T is the time for which Q has been observed, and H is the head, delta H. Basically, it is written. So it's a head difference basically we have taken to find out the hydraulic conductivity, and it is saturated. Saturated hydraulic conductivity measurement in laboratory condition by using constant head permeameter arrangement or permeameter method. Now there is a variable head as well. If we cannot maintain the constant head, we have another arrangement that is variable head. So the same soil sample here of same cross section area A, length L is subjected in the same way, but head is not maintained. This tube is supplying water with the initial head here, initial head that is H T1 at the time T1, and after certain time T it is reaching to here, that is H T2. So this discharge through this soil is happening because of change in these two heads HT1 and HT2. From where? From a reference point we are taking or measuring simply these two heads. So difference between these two heads simply is used to create the discharge. So that in time T is T2 minus T1 means simply time difference. So discharge total in time T is simply hydraulic conductivity K. K is the area of this sample, and HT1 minus HT2. Two heads are there, HT1 and HT2. So head difference and length of the or path of the flow through this soil, that is L, we have taken. However, this same will be equal to the volume of water that has been passed through this soil and it is reducing in this tube which is supplying water. So this rate of flow in this particular tube, or rate of fall of head in this supply tube, that is basically per unit time we are taking ds by dt. For the same time, if we are observing, and A, or say simply cross section area, this tube is A. So it is cross sectional area of the sample A we have taken here, and the measuring tube, or that is supplying water tube, cross section area is smaller A. So we can get for the same time or instantaneous time, let us say, this rate of fall of head for any particular time ds by dt, that is with area makes the volume. That is the simple idea. We can get Ka delta means Ht by L. That is simply we are taking into account this whole condition. So these two conditions, is it clear to you? Is it clear? Okay. So rate of flow Qt is equal to the rate of fall of head ds by dt multiplied by the cross sectional area of this tube that is supplying water to the sample. So once we have this relationship, rate of fall of water in this tube, supply tube, is simply equal to the rate of flow that is collected per unit time, is simply we are getting a relationship. A negative sign indicates that head decreases with increase in time. So head is decreasing. Now we need to find out for the T, 2T condition, T1 when it was started to T2 when we have taken this whole observation. So we can integrate these two equations with respect to head and time. So because it's a head here which is falling, and here it is time which we have observed as Qt. So we are simply integrating these two conditions for head from T1, Ht1 to Ht2, and this time from T1 to T2 that has been observed in this charge condition. So now, you know, by integrating this condition, you can get A, that is multiplier, and it is minus, so it is natural logarithm of Ht2 plus natural logarithm of Ht1. That is equal to now A, K, that is multiplier by L, and dt, that is simply T. So for T, it will be T2 minus T1. Now you can arrange these two. Since it's plus minus, then A natural logarithm of Ht1 divided by Ht2, because it's negative, so it will go down, and that is K T2 minus T1. Now we need to find out, our objective is to find out hydraulic conductivity by this arrangement, falling head permeameter apparatus. So K is equal to, by rearranging the terms, we can get K is equal to LA divided by A here T2 minus T1, and the same ln St1 minus St2. So if we have observations about head in supply tube or supply line from beginning T1 to T2, and at the same time we are measuring the discharge from the sample that is coming out after saturating it, that is hydraulic conductivity in this time T, that is T2 minus T1 minus T2 minus T1, then we can find out hydraulic conductivity of the soil in laboratory method. So in laboratory condition, we need to collect the sample from the soil by using the core. Core means it's a cylindrical shape of a certain diameter and certain length. We are pressing inside the soil slowly so that soil is not getting disturbed, and slowly it is taken out from this soil after cutting it, so that we are getting undisturbed soil. However, in general, once we are driving this core sampler inside the soil, there is pressure. We need pressure to drive it in the soil. and that makes a little disturbances to the soil here. And that's why it is preferred to take observations about hydraulic conductivity in situ condition, means in the field itself, so that we are getting the right information. And that's why there are number of methods. Yesterday I showed you. We can use any one of those to find out the hydraulic conductivity of the soil without disturbed condition or in situ condition. So now these two methods are practiced or used in laboratory condition after taking sample from the field. Now there are few applications, just two applications. You have already learned that we are considering this soil as a layered system. There are layers. Naturally, if you are seeing the vertical cut of any soil, it has different layers, and layers have different properties: texture, structure, compactness, and so on. So once we are taking into account a certain depth of soil, say starting from top surface here, 60 centimeter, root zone depth, where roots are distributed in the soil, or maybe near about 90 centimeter or 1 meter depth, soil has different layers which have different properties. The moment it is a layered soil, or usually soils are layered soils, it is different characteristics in terms of their behavior to allow water move through these. Just like hydraulic conductivity, the topsoil uses number of machinery to manipulate it for agricultural purpose, so it becomes more compact. However, it is manipulated every time, so it becomes loose as well. But the willow to this soil is always compact because it is not disturbed then after any time. So manipulation generally is done up to say 15 centimeter usual, but not more than 30 centimeter depth for agricultural purpose. So the soils are compacted at the top and further compacted below to that top soil. That makes a kind of different characteristic layers of the soil. And we need to find out, say, water movement phenomena or total water movement, maybe towards groundwater, maybe sometimes lateral condition. And that's why every depth, since we have differently, we need to find out what could be the total behavior or total condition of water movement from these layers. So in that way, we have applications of Darcilla, just like horizontal flow through layered soils. Usually soils are layered condition. Here simply I want to show you that there are three layer system which have depth D1, D2, D3, and let us consider, suppose we have measured somehow hydraulic conductivity as K1, K2 and K3. So how to find out combined characteristics of these layered soils in terms of its equivalent hydraulic conductivity, rather than taking K1, K2, K3, because our target is to find out at the last what is the discharge here in lateral condition. So there are conditions, suppose it is filled, suppose it's a big channel, reservoir, and it is filled with water. So water, it's not only vertical moving here downwards in filtering, but here as well it is moving in all direction. So the question is, water once entered into the soil in any direction, it will move again inside the soil in any radial direction. So we need to find out how much it is moving in this way and what is the amount that is going down vertical. So simple idea is horizontal flow through layered soils cannot be accomplished by using Darcilla. So assuming that there will be no flow across the boundaries, suppose it's a layered soil we are considering, so there is, suppose assume there is no flow in between, it is passing through these layers only, but it is not going just like this from one layer to another layer. So across the boundaries water is not flowing, between the individual layers and the hydraulic gradient for each of the layer, then we can say I, that is delta H by delta L, is simply difference between two layers. So what sorry different at 2 points, not layers, 2 points. So H2 minus H1 divided by L could be the hydraulic gradient for each layer, where L is the length of flow here we have considered for our understanding. And in that way, for each layer, we can calculate the rate of flow per unit width. You know that discharge Q is equal to, what is that? KIA. But it is unit width we are considering. So let us make this capital Q in place of a smaller q. K is hydraulic conductivity, I is hydraulic gradient, and in place of area we are considering per unit width rather than the whole width. So that is simply we are taking the depth into account. Depth into 1, that makes per unit width area. Is it clear? So in that sense, discharge from each of the layer per unit width maybe Q1, Q2, Q3 for these 3 layers, and we can give like Q1 is equal to K1, that is hydraulic conductivity, D1, that is its height or depth in terms of soil downward depth, and I. So 1 is everywhere, that is per unit width of these soil layers. Movement of water or discharge of water, Q1, we are simply considering here. So in that sense, we can find out for each layer or all 3 layers, Q1, Q2, Q3, or if there are more number of layers, suppose you are taking a practical example of particular place, you can have number of layers of different depth maybe. So you can find out for each layer what is the flow per unit width, we can find out. So Q1, Q2, Q3, K1, D1, I, K2, D2I, and K3, D3I, where K is hydraulic conductivity, D is the depth of every layer, particular layer, and per unit width we are considering, so area makes 1 into D, and I is hydraulic gradient, that is simply delta S by L. Now once we have for these 3 layers, we can add up to find out the equivalent or total discharge that is moving from all these layers or 3 layers, finally reaching here out as outflow as a Q. So Q1 plus Q2 plus Q3 discharge from these 3 individual layers makes the total discharge, that is Q. So what will be the Q? We can make Q1 plus Q2 plus Q3, and then we can add all these 3 functions, K1 D1, K2 D2, K3 D3, and all multiplied by hydraulic gradient, because hydraulic gradient at exact 2 points representing, suppose first point is here, second point is here, so everywhere it is having the same delta H, H1 minus H2. So that is delta H basically we are having. Why? Reason being, inflow is having the constant head condition, that is H2, and outflow is we are considering as a constant head condition for all 3 layers as outlet single condition. So in that way, we can have the equivalent discharge Q, Q1 plus Q2 plus Q3, and in this way we can add up all 3 layers characteristics of hydraulic conductivity based flow. So now this K is K1, K2, K3 for these 3 different layers. Let us have a single K, that is equivalent hydraulic conductivity for this combined 3 layer, or we can say whole depth of this soil. So what will be the K? Now in this term, Q is equal to, simply we can have K into D1, D2, D1 plus D2 plus D3, I. And if we are equating these two, we can find out K K is equal to simply K1 D1 plus K2 D2 K3 D3 divided by simply D1 plus D2 plus D3 because I is same here. So in that sense, we can find out hydraulic conductivity of layered soil when we are considering horizontal flow conditions. So horizontal flow through layered soil, the equivalent hydraulic conductivity K is simply K1 D1 plus K2 D2 plus K3 D3 or plus Kn Dn divided by D1 D2 D3 plus Dn, something like that on n number of layers. One practical example of Darcy's law to find out the hydraulic conductivity or equivalent hydraulic conductivity of layered soils. Usually, soils are layered systems. So we need to find out for precision what is the depth of layers and individual layer. If we have hydraulic conductivity, equivalent hydraulic conductivity, we can calculate back to find out more accurate results in terms of water flow or water movement. Is it clear?
Yes, sir.
Okay. Now, this was the case of horizontal flow. Now, what about the vertical condition? We have vertical flow downward for the same three layer system. For an example, we have taken D1, D2 and D3. Here we are assuming that their water was supplied from one side and it was going other side. Now it's a case of vertical downward flow in layered soil system. So water is supplied from the top, and let us make a condition like you have experimented that this is the soil from here to here, and this is the water which is filled, or this is a reservoir of water which is, or it is a flooded condition. So if we are measuring hydraulic head at the top of the soil, what will be the head, hydraulic head? It will be
Zero.
same amount, flooding depth. This is the first layer. So we are putting a piezometer here to measure the hydraulic head because it's a flooded condition above. So water will go above somewhere from the top soil. It is here. Why it is not reaching here to the flood level? It is saturated condition. Anybody? You have learned in soil technology the piezometers. Anybody? Can you explain or you cannot? Why you don't means recall it, something like that as well as it's possible. Anybody? I need to hear from you. Otherwise, I feel that you have gone for a cup of tea and I am sitting here. Then I need to find out the name. Yeah, Jaychand,
Yes, sir.
do you know what will be the level of hydraulic head in first layer, bottom of the first layer, if it is a flooded system?
No idea, sir.
It will be at the level of water or not? Because flooding, if we are putting as a simply tube at the bottom of water, it will fill up to the level of water. But if it is a soil, we are putting at the bottom of the same tube, we are, it will not reach to the level of water because of the voids present here. It's not water which is filled, but it's a void. That's why it is supporting a little bit higher, but it cannot reach up to the level of water. So this is the hydraulic head at the bottom of first layer. So it's a hydraulic head at the top of first layer. It is the hydraulic head at the bottom of first layer. That hydraulic head at the top of second layer. We are measuring hydraulic head at the bottom of second layer. That makes again hydraulic head at the top of third layer, and we are measuring by this fourth piezometer the hydraulic head at the bottom of this third layer, which is somewhere here. So this is basically the hydraulic head difference. From there we are estimating. To recall, laboratory experiment, falling head and constant head, it's basically head of water, that is called hydraulic head when we are measuring from this reference point. So from this reference point, hydraulic head at the top, this one, because this is floating. Hydraulic head at the bottom of first layer, it's somewhere here. Here you can see. So that's why it is H2 and so on. So we have these three layers with measured hydraulic heads at the top and bottom. This is top for second, bottom for second, top for third, bottom for third. So we have measured hydraulic head. We are simply trying to estimate the discharge or rate of flow considering each of layer 1, 2, 3. So Q will be the same because at the bottom, if it is water entering from the top, it will move through all these layers. It will reach at the bottom the same quantity. Quantity will not change, Q. So Q is equal to, from the first layer, that is having hydraulic conductivity K1, from unit cross section area of this soil, that is A, head difference between top and bottom. That's why it is flowing from the bottom. So H2 minus H1 or H1 minus H2 because of this head difference from higher to lower. So at the top it is H1, at the bottom of first layer it is H2. So H1 minus H2 and depth, that is D1. In that sense, since Q is constant from the lowest layer, that is third layer, so Q for the second will be K2, that is what we have assumed, hydraulic conductivity. A, same cross sectional area, that is unit A. And now at the top and the bottom head, so top head condition will be like this, H2, and bottom at the second layer will be like H3. So H2 minus H3 divided by depth, that is D1. In the same sense, third layer, discharge Q that we have measured at the bottom, hydraulic conductivity K3, same area A, and head difference at the top and bottom of this layer. So at the top, this is the bottom of second layer, so that makes H3, and the bottom of third layer, that has H4. So H3 minus H4. So in this way, we can have same discharge which is coming out from the bottom of third layer here in this our example. So Q is equal to K1A, K2A, K3A multiplied by the head difference between top and bottom positions or layers or points of each of the layer divided by depth of each layer. So assuming no lateral flow and no accumulation of water in the layer, means in this particular case we are assuming that there is no movement of water in lateral direction and there is no accumulation. Once it is saturated, means it's saturated. Addition of any drop of water or single amount of water will pass on from the bottom. So there is no accumulation of water and there is no lateral flow in this particular case we are assuming. So rate of flow through the cross sectional area A will be the same, which is coming at the bottom, and rate of the flow from each of the layer you can put like this. So these equations can be rearranged in terms of head and A condition. So Q, that is multiplied by depth once it is going in this side, divided by K1. So Q D1 by K1. In this form we are arranging all these three equations. And let us add all these three equations to find out the equivalent hydraulic conductivity of this example, particularly three layered soil system, to find out the equivalent hydraulic conductivity K. So once we have rearranged these equations in this form, Q dk, let us see. how they are getting added. So Q d1 by k1 plus Q d2 by k2 plus Q d3 by k3. So Q is common, Q into d1 by k1 plus d2 by k2 d3 by k3, and in right side condition what will happen? A is common, H1 minus H2 plus H2 minus H3 plus H3 minus H4. So simply it will be nully out and it will be H1 minus H4 simply. So this is the final equation. By adding these three equations, Q into d1 by k1 plus d2 by k2 plus d3 by k3 is equal to simply H1 minus H4 into area. So if we are rearranging this equation in the form same, Q is equal to K delta H by L into A. What is that? Then K is hydraulic conductivity. So delta H, let us rearrange this equation. Q is equal to, because Q is the final outcome we have observed. So Q is equal to, let us make this particular condition to here, d1 by k1, d2 by k3 and h1 minus h4 into A. We are taking a single term, that is D, multiplied as well as divided by D. And this D is the total flow path through the layered soil. That is, D is equal to depth D1 plus D2 plus D3. So Q is equal to, we can take, because we need to make this particular term as here, delta H by L. So we have delta H by delta H, H1 minus H4 in these three layer system. H1, that is at the top of the first layer and at the bottom of the first layer. What is that? That is H4. So we have head difference from the top to the bottom of this three layer soil system, H1 minus H4. So it is H1 minus H4 and equivalent are total depth of these three layers, D1 plus D2 plus D3, that is D into A, and this whole term whatever we are getting should be equal to now this K. So K is equal to D by D1 plus K1 plus D2 by K2 plus D3 by K3, and this is now the hydraulic conductivity of this three layered system, where we are considering vertical or downward flow of water. So we can have simply any layered system, D is equivalent depth of all layers plus something like dn by L. So we have depth of each layer, hydraulic conductivity measured layer wise. So we need to find out the equivalent condition to make it more precise information in terms of water movement in the soil system. So this is another application of Darcy's law to find out vertical or downward flow in layered soil system. Any query if you have?
Sir, can you once again explain why H2 is above the water level?
Oh,
Why
here,
why in that
this
capillary?
one
Yes, sir.
in this figure.
Yes, sir. Yes, sir.
Okay, what is your question? Why H1 here
Sir,
is
H2
above the H2
H2 is
is above this? Okay,
yes.
this is saturated system. Is not that we are considering soil is saturated? True.
Yes. Yes.
Suppose it is a, let me take it this way. This is a pot, say simply first, and it is filled with water. I am putting a tube here. What will be the level of water in this tube? I think the same water level. Is not that?
Yes, sir.
There is a bucket or there is a, say, pot which is filled with water and we are putting a tube inside it. What will be the level of water? The same water level in this tube? Yes or no?
Sir, I I
It's,
think the same. Maybe.
don't think, means be confident. What about others? Anybody? Other friends can support? It appears that nobody is there, only login. They have locked in and gone out.
So, sir, it
Is like that?
top one.
No. Question is whether this will be at the same level of water or it will be different.
Same.
Different, sir.
Hey, bhai, what do you want? I should not ask any question. इतना disturbance करोगे तो question कहाँ से पूछा जाएगा? Okay, so what are you telling? It will be the same level or different level? A bucket filled with water. We are placing simply a tube. So what will be the level of water inside that tube? What is the answer?
Same level, sir.
Sure, na? Are you sure?
Same.
Say yes, man. Same level, sure. Okay. Now I am replacing this water filled bucket with the same bucket filled with soil. And it is saturated. Saturated means pore spaces are filled with water. What will be the level here of water now? You have learned in soil technology. Voids are filled with water. I am telling you that soil is saturated. Saturated means what? Void space is filled with water. Are you sure or not about this statement?
Yes, sir. Voids are filled
Okay.
with water.
Then filled with water. Then what will be the level of water here in this tube? Tube is still there. Same tube. You need to tell. You need to speak something. Otherwise, it's disconnecting to me. Disconnecting means not network disconnecting. Means it's a thinking process disconnection. What will be the level? It will be the same level of the soil, or it will be less, or it will be more. What is your idea?
Less from previous, sir. Less.
Less. Why it is less? This is the question. Why it is less? Reason being, it is only the voids which are supplying water, right? And there is a percentage. I told 30 to 60% are void maximum. So means only just somewhere 30 to 60% of water which is reaching to this tube remain in the soil. So it cannot be filled up to the same level. Now the question is, suppose I am adding on to this, I am adding water here again, flooding, just like paddy fields. You recall it? Paddy fields. So this is soil, and above to this water is flooded. What will be now this new level of water in this tube? Anybody?
Bit increment.
That everybody knows. My question is whether it will be at the level of water here or it will be below this water level.
It will be somewhere in between, like not to the level of water.
You are in hostel or you are in at home?
I'm in hostel, sir. In the room, some work is going on.
तो उसको बोलो कि थोड़ी देर मेरा क्लास चल रहा है. Just go out. It's your class. You are not getting disturbed.
Sir,
So
yeah,
the question is, yes?
work started just now, like अभी तक नहीं.
Work started doesn't mean that it will disturb you. You have all authority to say no for now. If somebody is disturbing me during I am taking class, I cannot bear it. Okay, let us concentrate about our learning rather than I am giving you my idea how to control the things. Okay, so we have filled this water. The question is whether water level will reach to this level of water here in this field, or it will be below, or it may be over. What is your answer?
Below.
Below. It's a simply below because it has effect of soil as well. So in the same way, here you have asked that in first layer bottom, pressure head will be, because this is flooded water here, right? So in the first layer, top of the first layer, because it's flooded, water level is same. So this is H1. From where? This is the reference surface we are measuring the head of water. So it is called the hydraulic head. Let me show you. Yes, here I showed you yesterday. This is datum. Datum means reference. What is hydraulic head? Here. From the datum to the water level. Basically, it is elevation head plus pressure head plus velocity head. But because it's soil water, Reynolds number is very low, velocity of flow is very low. So it is only elevation head and pressure head. Some of these two. That is called the hydraulic head. Don't get confused. Datum is not always here. We can take the soil surface as well as datum. So it will be again elevation head from here to here. That will be negative. This will be pressure head. So if you are, it will be negative, it will be positive. So if you are making a difference, it will come the same. So hydraulic head means difference from datum to the water level. So if you are making the reference here, it will be hydraulic head considered like this. For all observation, it will be the same then. So that is the basic idea here. We are simply finding out what will be the hydraulic head here. So at the top of this soil layer, it will be the same level of flooding. At the bottom of first layer, it will be, because it was flooding at the top, so certainly it will be a little more. Or maybe somewhere here. It's a matter of measurement. So now did you get? It was a question why it is H2 above the level.
Yes, sir. Yes, sir.
So it is clear now.
Yes, sir. It is
Any
clear.
other question? Any other question, query? Anybody? No question? Should I assume that you understood it properly? There is no query. Say yes or no, at least.
Yes, sir. It is clear.
Okay. Now, so you learned two processes, infiltration and hydraulic conductivity. The first process is to find out how much water it is entering into the soil. And second process tells you how much water is passing through the soil because of head condition or hydraulic head condition. Now, somebody asked at the beginning, what is the effect of soil moisture on hydraulic conductivity? Do you recall this? Who has asked? I want to know. 2 days back, I think it was in Monday class. Somebody asked me that what is the effect of soil moisture or saturation on hydraulic conductivity? You couldn't recall, or you forgot your question as well. 43 students are there. So the question who has asked is not present in my view then. Who has asked this question? That is the drawback of online teaching. Deepak? Jayachan? Ankit?
Yes, sir. Yes, sir. Jai Chandra is here. No, sir. I was not the guy who asked the question.
Okay. So let me tell to you all guys. What we have discussed, it is saturated hydraulic conductivity. Yes or no? So water moves when soil is saturated. But do you think water is not moving when soil is not saturated? It is, water is moving in capillary form, that is unsaturated, and so on. So hydraulic conductivity is simply the rate of flow of water through medium. If then there must be condition for unsaturated movement of water in soil. That is for sure. So usually we cannot measure the unsaturation condition movement of water in soil. We are simply measuring the saturated condition of water movement in soil. That is saturated hydraulic conductivity. But we are estimating unsaturated movement of water conductivity in water. That is called, so this is Ks is hydraulic conductivity at saturation, and K theta, that is hydraulic conductivity of moisture in soil under different moisture content. It is only saturation, but it is theta, that is saturation, soil moisture content. And now there is a relationship. This is the saturated hydraulic conductivity Ks, and this is say soil moisture content theta. It is melting point 0, and it is suppose saturation. That is clear. So once soil is very dry, it is say melting point condition, or if we have measured the pressure or say soil moisture suction condition in soil, it is minus 15 atmospheric pressure here, and at saturation it is 0. Somewhere it is a field capacity, and whatever moisture content theta you want to. So once it is melting point range soil characteristics, if we are applying water to the soil, suppose this is again soil, we are suppose applying water on this soil, so it is completely dry at melting point characteristics. What will be output at the bottom of this soil? Q will be 0. Yes or no?
Yes, sir.
And what is hydraulic conductivity? When soil sample is subjected to hydraulic head, there must be flow. So at this melting point soil moisture content, there is no outflow, so hydraulic conductivity is 0. After some time, water will reach here, it will come, and a portion of water will come out because of gravity. So it is say amount x1 beginning, but it is coming out just like say initially drop by drop, something like that. So it will be some conductivity, means some conductivity from this soil, so little water comes out. After some more time, moisture will increase, pores will be filled up to greater extent, and then water will come a little more, and so on. So it is reaching at a certain point here. Please ignore this. Like this. So once it is saturated, it is constant and maximum. So hydraulic conductivity versus soil moisture content, once it is saturated, that's why it is saturated hydraulic conductivity, it is constant. And then after, no matter whatever it is level of water, it is constant. Reason being, you cannot increase water content inside the soil after saturation. So hydraulic conductivity is maximum and constant here. But before that, it is less than this constant condition, which is at saturation. And if moisture reduces, it is reduced conductivity of water from this soil. So this is basically the relationship between saturated hydraulic conductivity and soil moisture content. Our hydraulic conductivity simply versus moisture content. When soil is saturated, hydraulic conductivity is constant and maximum. So this is basically the relationship you have asked or somebody asked that day, and in this way we are relating this. Is it clear now?
Yes.
Anybody? Okay. Now you have learned that if it is soil surface, water is either raining on this surface or it is supplied through irrigation requirement condition or irrigation water. Water is spreaded over this surface and starts entering into the soil, that is infiltration. then it is moving inside the soil, and once it is saturated, it is all pores are filled with water theoretically, and then water moves below this level where we have interest, and this is called the root zone depth where we have our interest. So it's important next to find out what is the moisture content of the soil, because we are not thinking about to reach to the saturation level. Reason being, in irrigation, we are interested to go up to the field capacity level from where plants are taking water. If it is in this region of water availability, plant cannot take water. Saturation water cannot be taken by the plants. So next part is to measure the soil moisture content. And that's why next discussion we will be starting on soil moisture measurement. Show you soil moisture measurement. So you have class after this?
Yes, sir.
Okay. So infiltration, hydraulic conductivity, I will update or upload these files in PDF form to you for your learning. And next time we will discuss about soil moisture and also water conveyance and control or water measurement in the farms. We need to finish these two aspects next week. Okay. So if you have any query, you can ask. Otherwise, you are free to go to next class, and we will discuss this topic, soil moisture and soil moisture measurement, on Monday. Any query? Anybody? No question. Deepak? Deepak Kumar.
No, sir.
Okay. So have a great learning, and we will meet on Monday to discuss this next aspect of soil moisture and measurements. See you on Monday then. And Monday we will have another lab as well. That will be hydraulic conductivity measurement, and I will send the files through ERP mail to you. Okay?
Okay, sir.
Okay. Have a nice time. Okay. Then bye.